This is Mark with your Advanced Assembly Technology Minute.
Hi, I'm Mark with Advanced Assembly. On today's edition of Mark Voids a Warranty, I'm going to take apart a $40 digital projector. Inside every electronic device are engineering tips, tricks, and travesties that we can use to make us better engineers. So let's dive in and see what treasures and travails await. The first board to come out of this device is a 9-switch and 2 LED control interface that operates off of just 5 conductors. The designers took advantage of an old trick that connects all switches to the same input line. Each switch connects VCC to the input through a unique value resistor. That provides a specific voltage that might be directly interpreted on an analog input line or with a voltage-controlled oscillator that feeds a digital frequency counter input. This is a very simple board, but the backside shows a single off-board connector and a tiny bit of silkscreen. A small amount of money might have been saved if the designers could have found a way to move the connector to the front side and do away with the backside silkscreen entirely. As the disassembly continues, we can see 3 printed circuit boards in total, 1 power supply, 1 logic board, and the control interface we saw earlier. The boards are spaced far from one another. Whether they need to be or not, there's plenty of room to do it in this design, so it's one idea to keep the power supply from interfering with the logic board. There's not much to say about the optics inside the device. It appears that light is diffused through a pair of Fresnel lenses onto an LCD screen. The light from the screen is then projected onto an exterior surface with a set of focusing optics. Optics lie outside the training of EEs, so most of us would have to depend on an external firm, such as Toshiba or maybe even Sunny Optical, to design and fabricate the optics. Projectors need a lot of light, and no matter how efficient modern LEDs are, they still produce a lot of heat. To dissipate large amounts of heat, many engineers turn to heat pipes. Copper only conducts around 400 watts per meter Kelvin. Heat pipes take advantage of phase change to conduct tens and hundreds of thousands of watts per meter Kelvin, an almost incomprehensible increase in efficiency. The power module does a good job of keeping all the components on the same side of the PCB, and the inductors positioned mostly at right angles to each other. There are plenty of ground stitching vias that prevent unintentional radiation. One thing I don't understand, however, is the purpose of all these hassle pads on the backside of the PCB. They all appear to be connected to the ground pour, and it's on thin copper, so I can't imagine they're used for copper thieving during plating or even testing after assembly. It's possible they serve a purpose as solder thieving pads for wave reflow, but I'm really not sure. If you know, please leave a comment below. Finally, let's take a look at the logic board. The designers did a good job of keeping most of the differential pairs running in short paths from the source to the destination. Routing this many digital lines is no small feat on a 2-layer board, and when comparing one layer to the next, you can see that they went to great lengths to ensure that all traces, even angled ones, pass perpendicular angles on adjacent planes. But if you look a bit closer, you'll notice some mistakes. The first issue is that the differential pairs from the top layer don't have a predictable return path below. Differential pairs need a copper path, or they will find one of their own and create radiated electromagnetic interference. This could be avoided by connecting the bottom copper layer to a few purposefully routed copper slivers on the top layer and connecting them with vias. Etched coupled returns aren't as good as planar return paths, but they're better than nothing. The second issue has to do with the vias. Return paths need to be designed in 3 dimensions. So when the signal transitions layers, there should immediately be adjacent return vias right next to them. Altogether though, there's a lot of engineering in this little $40 gizmo. I like it. I hope you learned something. We'll see you next time.
If you liked this video, let us know by clicking the like button at the bottom of the screen. But don't stop watching now. We have other educational and informative videos on this channel. To learn more about what Advanced Assembly offers and how we can help you, please visit aapcb.com.